Okay, we're going to talk about moisture this week, and then we're going to talk about clouds and precipitation, things you're all probably kind of interested in. So let's look at right now our current weather map just to talk about moisture. And a measure of moisture is something called dew point. We'll go into more detail about what it is in a little bit. So if you look at the dew point, the bottom left number on the station symbol, notice over Ohio right now, dew points are in the mid 50s. Fairly dry for this time of year, actually. If you look over here along this front, notice the dew points are in the mid 70s south in the warm air. So quite a decent amount of moisture there. And you can go across the whole country looking at this. For example, right now there's somewhat of a monsoon that's been setting up out in the New Mexico area and stuff. And you can see dew points in the 50s out there, which for them is fairly moist. And you can see dew points coming up into the middle section of the country in the 60s here, southerly wind. So where does this moisture come from? Well, if you look at a GOES satellite, this is a moisture channel. It kind of measures moisture about 700 millibars or 15,000 feet up. Notice moisture coming up from the Gulf of Mexico into the eastern part of the United States. The yellow area is fairly dry, so we have a lot of dry air out here right now into the mid-level of the atmosphere. Notice also into the like Arizona, New Mexico, there are clouds and moisture coming up literally from the southern Pacific. Doesn't happen in the wintertime. This is a phenomena for the summertime. It's a monsoon that sets up and gives them some moisture. So with that, let's delve in to just what we're talking about with moisture. So we're going to talk about humidity, saturation, and we're going to touch on stability, which can be a confusing topic, but we'll hope it won't be. So there are things called atmospheric rivers. We just looked at how the moisture flows from different parts of the world to other parts of the country. I mean, like out of the Gulf of Mexico and up to the East Coast or out of the Pacific. Atmospheric rivers are just long stretches of moisture. And you can see these sometimes in the wintertime where they'll stretch all the way from Asia to North America. And you see this large mass of moisture being pulled across the Pacific, coming into the Pacific Northwest. That's when they get a lot of rain. Sometimes even in the southern part of California. They need that right now, with how dry they are. And you can see how these can cause lots of moisture and lots of rainfall. So the total amount of water in the atmosphere is actually really, really small. And most of it's confined right into the troposphere. Hardly any is above the troposphere. All water vapor were removed. You get about 1 inch of water everywhere across the globe. Not a lot. So water continually enters it through different means. So here is a look at that. So over the ocean, there's evaporation that takes place, pulling moisture up into the atmosphere. Happens with lakes too. You get it with Lake Erie, for example, near you all. It can happen off of snow with sublimation. We've talked a little bit about the change of states, and both of those are transports, ways of getting water up into the atmosphere. And then the atmosphere can move it. We've talked about wind now, so we know the atmosphere moves around, carries the air. So that's how this moisture moves. So, oh yeah, trees. There actually have been studies, believe it or not. Somebody was interested and wanted to know. The dew points in Oklahoma vary tremendously in the summertime. The early part of the summer, dew points might be in the 60s, even almost to 70. And people were curious why that was, why they were so much different when they fall back into the 50s in the latter part of the summer. Well, what happens is they discovered winter wheat. Evapotranspiration, or transpiration from the wheat, was sending moisture into the air, so that once they cut the wheat, the amount of moisture in the air significantly decreased. So it's an interesting impact. that plants have on this. Oh yeah, and then the precipitation falls out of the clouds. It can fall on a mountain and may run off very quickly. It can fall on a flat land. Maybe it'll stay there very slow to move out. Some of it filtrates into the ground. That's what helps keep our water supply so we have water to drink. And some of it flows back into the ocean to the rivers and all. I was out my western trip and I went over the Continental Divide probably 8, 9 different times as I was driving across the section. And that Continental Divide divided where all the water that hit one side would flow towards the Pacific, and all the water that hit towards the other side would flow towards the Gulf of Mexico or the Atlantic Ocean. Kind of interesting. We've talked about changes of state with evaporation, where molecules vapor enters the atmosphere, condensation, where they go back into a liquid state from a vapor, and transpiration and evapotranspiration. Sublimation is ice and it just goes right straight into vapor. It happens in the wintertime all the time. And sometimes vapor deposited right onto solid, becomes like a frost in the wintertime. And precipitation can form in all different types of precip. So humidity is a way we kind of measure this. And we have, as meteorologists, we like to look at them a lot of different ways. Because one of the most important things a meteorologist does is track moisture. So you know if it's going to be a cloudy day and if it's going to rain, snow, sleet, whatever. That's probably what you're very interested in. So we have something called vapor pressure. Water vapor is a gas. So it's going to have a pressure like any other gas. And notice it makes up no more than 4% of the atmosphere in the lowest kilometer. So it's way down low, most of this. Mixing ratio is a ratio of water vapor per mass to the remaining dry air. Key point here is to the remaining dry air, whereas specific humidity is all the air that was in that section that they were using to estimate. So they're close, but they're not equivalent. And absolute humidity is the mass of water vapor per unit volume of humid air, or normally expressed as grams. Saturation is when the air can't hold any more water vapor. If it got any more water vapor in, some of that water vapor would have to become liquid. So, in order for that to reach that point, like clouds are saturated air, rain, again, pulling out the moisture. So all we've done for all those terms I just mentioned, we just add saturation to them. So changing the air temperature disturbs this equilibrium. The hotter the air is, the more moisture the air can hold. So the idea is that the molecules are spread a little bit further apart when that happens, so they can hold more water vapor into that area. And the colder the air is, the less water vapor they can hold. And there is a difference between ice and liquid. When you get near the freezing level, what happens is liquid, the molecules are still moving fairly quickly. So the saturation vapor pressure is one thing. On ice, the molecules have slowed down significantly. So instead of molecules of water escaping from the ice as easily, they don't. So the saturation vapor pressure is always going to be lower over ice than it is over water. So that anytime you're in an area that's getting ice, the water vapor is going to tend to go towards the ice and make it grow. Relative humidity is what we're familiar with. And all that is percent how much water can that air hold. The higher the relative humidity, the less water it can hold. The lower the relative humidity, the more water it can hold. If you're out in the West Coast under a Santa Ana wind where it's coming down off the mountains, the air is getting hot. There's very little moisture in it. And as that air gets hotter, it can hold more and more moisture, but the relative humidity keeps going down. And there have been times in those events where the relative humidity is 2, maybe even 3%. Now, if it's raining outside, there's a good chance the relative humidity is 95 to 100%. So we talked about temperature making the relative humidity go up if it's colder and down if it's lower. So that's why, think about it, we get fog more in the morning than you do in the later part of the day. Well, the temperature is the coldest in the morning, so there's less ability to hold moisture in that air now. So it changes and may become fog. Then in the afternoon, when it heats up, the relative humidity will drop. I wanted you to notice just a little thing here. There's a little spike in the humidity here in the evening. Kind of goes back up a little bit. That is when most of the plant life gives up its moisture into the air that it's absorbed during the day. So that's why that spike occurs there a little bit. Dew point is just another measure of this moisture, and it's something that's right on the weather map, and it's something that all meteorologists look at to see. Well, the idea is dew point directly relates to water vapor content of the air. The higher the dew point is, the more water is in that air. So if the dew point and the temperature are close to each other, it means the air is very close to being saturated. If they're far apart, it means it's very dry. So you can see the difference in dew point. Say in the wintertime, look at it. Your average dew point is only less than 20 degrees Fahrenheit. In the summertime, your average dew point in Ohio, 60s. And where I live, it's close to 70. And it does. And last week, we've had almost every day we had dew points pretty consistently in the low 70s here. Didn't rain, but we had dew points there. So one of the interesting things about knowing the dew point and the temperature is when they get closer and closer together, you expect clouds to form. So how do we get them closer together? Well, air rises, it cools. If it's cooling, it can't hold as much moisture. So the temperature, colder it gets, the closer it's going to get to the dew point, because we haven't got rid of any of this moisture as the cloud air is rising. So they wind up becoming saturated. That's how the clouds would form. Do the other thing, like happened here today, all of a sudden our winds started coming off the Atlantic Ocean. And it's quite cool. It's only for us, temperature is about 71, 72. Guess what? The Atlantic Ocean right now is 71, 73 in that range. So we're getting all this moisture coming off the Atlantic in here, and our dew points and temperature are almost identical. And we have clouds, and we're getting light rain. Now we're going to talk about stability. I want you to understand this because you're going to be seeing it several different places. It's a key point to why air moves. Think about an air parcel. An air parcel is just, say you were to put a bag around a bunch of air. That would be a parcel of air. Say you had a big balloon around a bunch of it. Maybe that would be a parcel of air. We're not interested in the size, but it's some quantity of air. You define it. If that air parcel has a tendency to want to go down, not from any other force, that just wants to sink on its own, that is stable air. Why would it want to sink on its own? Well, we know that colder air is denser than warmer air. So if that air parcel is colder than the surrounding air, it's going to want to sink. If that air parcel is warmer than the surrounding air, it's going to want to rise. So why would it be different? All the air is the same, right? No, it's not. The air changes temperature as it goes around, and there's something called a change in temperature with height, which we talked about earlier. Generally, that is very close to around 7 degrees Celsius per 1,000 meters. That is not the dry adiabatic lapse rate. That is not the moist adiabatic lapse rate either. It's between the two. Some days that might be 8 degrees. Some days it might be 6.5 or 7. It varies. If you looked at an upper air sounding, you could calculate it and see. The steeper the temperature goes down, the steeper the lapse rate is, the easier it would be for a moist air parcel to want to keep rising. Why is that? Well, let's take a look at a moist air parcel. If an air parcel is moist, it's cooling at 6.5 degrees. So if the other air is cooling at 7, that air parcel is consistently a half a degree warmer than the surrounding air. So if something started that air parcel moving, maybe it was the heat from the ground, maybe there's a cold front coming in. Whatever started it to lift, it's going to keep going faster. Now, if that same air parcel is unsaturated, then it's cooling at 9.8. Temperature outside is 7. As it's going up, all of a sudden, at 1,000 meters up, it's 2.8 degrees colder. So what's it going to be trying to do? It's going to be trying to sink. So that's called stable air. And there are absolute or conditional instabilities, as we've talked about here with that. And things that cause air to rise: sun heats the air, makes it expand and rise upwards. Mountains. I saw that a lot when I was out west. One side of the mountain have the wind coming into it. Man, that air went up. Other side of the mountain had the air coming down. No rain. Warm fronts and cold fronts. And there are rain shadows, for example, with all of this. Winds converging together around the low pressure system. They tend to come together. Or sea breezes can push in and push the air up. So that's all about the moisture. So hope you got some of that. Please let me know if you have any questions about this one.